to Projects. In this video, we are going to explain about the project, which is real-time prognostics and health management without run-to-failure data on railway assets. Introduction of the project. The project highlights the significance of prognostics and health management, which is PHM, as a technology that performs data and health states into actionable information. Originally rooted in the aerospace industry, PHM is now explored across diverse sectors such as manufacturing, automotive, railway, and heavy industry. The project underscores the motivation for employing PHM, emphasizing its potential to significantly reduce support and operating costs while enhancing safety. An illustrative example of a railway incident due to poor maintenance highlights the critical need for effective prognostic strategies to prevent accidents and maintaining public trust in industries. The project addresses the challenge of predicting the remaining useful life, which is RUL, and health of critical railway assets such as electronic devices and motors without relying on abundant historical run-to-failure data. The absence of extensive data sets poses a risk to traditional machine learning models in accurately forecasting faults, potentially endangering human lives. The project employs K-means clustering algorithm on DTW values to categorize motors into distinct clusters, working motors from clusters with normal and flat curves, while faulty motors exhibit clusters with noticeable deviations. The clustering facilitates the identification of faulty motors based on their distinct characteristics. Objective of the project. The objective of the project is to develop a system capable of providing real-time prognostics for remaining useful life, which is RUL, and health of critical railway assets, specifically electronic devices and motors, without relying on extensive historical run-to-failure datasets. Implementing a data analysis strategy that makes use of live motor current data obtained from Kaggle prognostic dataset. The project aims to enhance the authenticity and relevance of the models, providing a more accurate representation of the current state and performance of railway assets. Goal is to utilize dynamic time wrapping, which is DTW, to measure the similarity between current motor data and historical records, enabling the identification of potential faults based on deviations in the similarity metric. The aim is to apply the K-means clustering algorithm on DTW values to categorize motors into clusters, distinguishing between working motors and those exhibiting faulty behavior. This clustering approach enhances the precision of fault detection. The aim is to predict the remaining lifetime of motors by calculating median time differences with each cluster. Use this information to schedule maintenance or replacement, ensuring timely interventions to prevent failures and enhance overall system reliability. To implement this project, we need software and hardware requirements. Coming to hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. The first step is importing the packages. In this module, it allows importing essential Python libraries and packages. We have imported NumPy for numerical operations, Pandas for data manipulation, Seaborn and Matplotlib for visualization, Scikit-learn for machine learning, and other relevant libraries for specific tasks. The next step is data exploration. In this module, the project explores the prognostic dataset. It involves loading the dataset, examining its structure, checking for missing values, and gaining insights into the features and their distributions. The next step is calculating DTW, which is dynamic time wrapping. It is a method to measure the similarity between two temporal sequences that vary in speed. In this context, DTW is applied to quantify the similarity between the current motor data and historical records, emphasizing dynamic changes over time. The next step is applying K-means on DTW values. K-means clustering is employed on the DTW values obtained in the previous step. This technique groups similar data points into clusters, allowing the identification of patterns. In this project, it is used to categorize motors into clusters representing distinct behavior. The next step is visualization. Visualizations are created to represent the clustered data. This involves plotting graphs where each cluster is visualized differently. Visualization aids in interpreting the results and identifying patterns, especially regarding faulty and non-faulty motor behavior. The next step is data pre-processing. Here we have two sub-steps. Coming to removing null values, here Missing values in the dataset are handled by either removing or imputing them. This ensures the data used for training and analysis is complete. The next substep is label encoding. Categorical data, if it is present, it is encoded into numerical values using label encoding. This step ensures the compatibility of the data with machine learning models. The next step is appending features to X and target to Y. The data is split into features as X and the target variable as Y. Feature represent input variables and target is the variable to be predicted. This separation prepares the data for training process. The next step is train and test split. The dataset is divided into training sets and testing sets. The training set is used to train machine learning model while testing set is used for assessing its performance on unseen data. The next step is building the model. The machine learning models are initiated and defined. Parameters are set up, determining the model's architecture and behavior. The next step is training the model. The model is trained using the training dataset. It learns patterns and relationships between features and the target variable, optimizing its internal parameters during this phase. The next step is user gives input. The project allows the user to input the data, simulating the current state of a motor or asset that needs prognostics. Given input is pre-processed. The user-provided input is pre-processed to ensure that it aligns with the format expected by the trained model. This involves scaling numerical values, encoding categorical features, and any other transformations needed for compatibility. The next step is predicting with the trained model. The pre-processed user input is fed into the trained model which generates prediction. For instance, it predicts whether the motor is faulty or estimates it remains useful life based on the input features. The last step is final outcome is displayed. The project displays the final outcome of the predictions. This is the classification result. The displayed outcome provides valuable information for decision making in maintenance or replacement strategies. Algorithms which are used in this project are K-means. K-means is a clustering algorithm that partitions a dataset into K distinct, non-overlapping subsets which are clusters. Each data point belongs to the cluster with the nearest mean, and the algorithm iteratively refines these clusters to minimize the sum of square distances within each cluster. K-means is applied on dynamic time wrapping values to categorize motors into distinct clusters. This helps identifying working motors which are clusters with normal curves and faulty motors which are the clusters with deviations. The algorithm's simplicity and efficiency makes it suitable for distinguishing patterns within the data. The next algorithm is random forest. It is an ensemble learning algorithm that constructs a multitude of decision trees during training and output the mode of classification or mean of regression prediction of individual trees. It introduces randomness to each tree, enhancing robustness and reducing overfitting. Random forest is used in this project for classification tasks or ensemble learning within the project. Its ability to handle multiple features and maintaining high accuracy makes it suitable for complex datasets, possibly aiding in fault identification and prediction within railway asset prognostic system. As an extension, we have used K-means, tuned K-means with various iterations and tuning parameters till to get better score. And we have employed ensemble model for improving the accuracy. Also, as an extension, we have used Flask and SQLite for user testing and authentication. We have evaluated this project using different evaluation metrics which are accuracy, precision, recall, and F1 score. This is the accuracy comparison graph. Here on x-axis we have accuracy score for each algorithm, and on y-axis we have algorithm names. Accuracy is the ratio of correctly predicted instances to the total instances. It provides an overall assessment of model's performance, considering both true positives and true negatives, measuring how well the model correctly identifies both working and faulty motors. This is the precision comparison graph. Here on x-axis we have precision score for each algorithm, and on y-axis we have algorithm names. Precision is the ratio of true positives to the sum of true positives and false positives. It assesses the accuracy of positive predictions, which is specifically identifying how many of the predicted positive instances are actually positive. It indicates the accuracy of the model in identifying faulty motors without falsely flagging non-faulty ones. This is the recall comparison graph. Recall is also known as sensitivity or true positive rate. It is the ratio of true positives to the sum of true positives and false negatives. It measures the model's ability to identify all relevant instances, capturing how many actual positives were correctly predicted. It assesses model's ability to capture all faulty motors, minimizing false negatives. This is the F1 score comparison graph. F1 score is the harmonic mean of precision and recall. It provides a balanced assessment of a model's performance, especially when there is an imbalance between the classes. It balances precision and recall, providing an overall measure of the model's effectiveness in fault detection. The model, which performs well among all these metrics, will be used for final prediction. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the dataset folder. We use this dataset for training the algorithms. These are the parameters of the data. And here we have classes, which are represented as A, B, etc. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is the app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. This is the model file which contains algorithm information and that will be loaded into the project code during runtime. This is the IPYNB file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the sign-up file. This file is a database file used to store the user information. Now to execute the project, we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folder's path. Here we need to type the command python space app.py and then click on enter. This will compile app.py file, and this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the localhost, and the port unless configured differently. This is the localhost and this is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. Here we can see the web page of the project is displayed in the browser. This web page is built by using the Flask framework. Here we can see a sign up link. First we need to click on it and enter all the sign up details if you are signing up newly. I have already signed up and I have an account in it, so we'll directly click on sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password. And now we need to click on sign in. We have signed in successfully. Here we can see the parameters which are need to be entered. Based on the given parameters, we will get the prediction. Now we will enter all these parameters. Before entering the parameters, we will understand them. Here we have data number. It represents a unique identifier or the index for each data entry, allowing for tracking and referencing individual records within the dataset. This is current. It refers to the electrical current flowing through the motor, serving as a critical parameter for assessing the operational state and health of the motorized component. This is flow rate. It indicates the rate of the fluid or material flow within the system, providing insights into the efficiency and performance of the machinery. This is time. It represents the temporal aspect of the dataset, indicating when specific measurements were recorded. Time is crucial for tracking changes in the parameters over the operational lifespan. This is RUL, which means remaining useful life. It signifies the estimated remaining operational lifespan of the asset or the motor, offering insights into when maintenance or replacement might be necessary based on predictive modeling. This is dust feed. It represents the quantity of the dust or particulate matter introduced into the system, which is a parameter that may impact the efficiency and health of the machinery. This is sampling. It indicates the method or frequency of data collection, providing context on how often measurements were taken and influencing the granularity of the data set. Now we will enter all these parameters step by step. So the data number is 10. Current value is 78.3573. Flow rate is 84.7349. Time is 77. RUL is 59.111. Dust feed is 54.1. Sampling value is 10. Now we will click on predict. Based on the given parameters, it has predicted as bias type A and level 1 is stage fault, which means here bias suggests that the prediction is related to a specific type of bias within the system or machinery being analyzed. Here, the term level 1 stage fault indicates that severity or the stage of the fault. Here it is specifying a fault type is level 1. Now we will enter other machinery details and see what will be predicted. So the data number is 4. Current is 35.69. Flow rate is 84.56. Time is 86.5. RUL value is 59.111. Dust feed is 40.3. Sampling value is 10. Click on predict. Here it has predicted as bias type is B and it is at level 2 stage fault, which means the machinery is level 2 stage fault. Now we will enter other machinery details and see what will be predicted. So the data number is 30. Current is 247.259. Flow rate is 81.78. Time is 72.4. RUL is 59.111. Dust feed is 57.8. Sampling is 10. Click on predict. So it has predicted as the machinery is bias type is D and level 4 stage fault, which means the machinery is at level 4 stage fault. Now we will enter other machinery details. Here data number is 28. Current is 4.66. Flow rate is 83.917. Time is 38.2. RUL is 177.31. Dust feed is 95. Sampling is 10. Now click on predict. So it has predicted as bias type is C and level 3 stage fault, which means the machinery fault is at bias type is C and level 3 stage fault. In this way, if we enter all the required parameters of the machinery, then the system will predict at which stage the fault of the machinery is. Now we'll click on sign out. Conclusion of the project. The project successfully validated the innovative approach of utilizing real-time motor current data from the Kaggle, which is prognostic dataset, showcasing its effectiveness in providing accurate and timely prognostics for critical railway assets. Through the application of dynamic time wrapping and k-means clustering, the system demonstrated high precision in identifying faults by measuring similarity and categorizing motors into distinct clusters, effectively of distinguishing faulty from operational units. The system's ability to predict remaining lifetime through the median time differences within clusters, providing reliable, enabling proactive maintenance or replacement decisions and contributing to overall system reliability. The integration of real-time data and advanced analytical techniques not only improves safety by identifying potential faults early, but also enhances operational efficiency by allowing for targeted maintenance interventions, minimizing downtime. The project's methodology and algorithms showcase scalability and adaptability, making them applicable to various critical assets beyond railway systems. The success of the project sets the stage for broader implementation in predictive maintenance across different industries, ensuring the longevity and reliability of vital infrastructure.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.